Hello everyone. In this video we're gonna go through the generation and propagation of action potential in pacemaker cells, and then later on we're gonna have a look at the action potential in contractile cells. So pacemaker cells are these specialized cells that can autonomously generate an action potential, and they form the conduction system of the heart. This conduction system is to be considered almost like a highway system for an action potential, where it travels through it really fast. But how is this action potential generated? So I've got this graph here, and in the y-axis you see is the voltage, so it's going to be in millivolts, and on the x-axis it's going to be in time, so roughly in milliseconds. And at the bottom I have that little elliptical drawing represent one of my pacemaker cells. So let's start by putting some references on this graph. At the bottom here, I'm gonna draw some potassium, and down here represents minus 92 millivolts. The reason it's minus 92 millivolts with potassium is that if there was only potassium going in and out of the cell constantly, this is the resting membrane potential that potassium would want it to have if potassium was the only player. Next one, we're gonna put sodium, and we're gonna put it up here, okay? And it's gonna be a plus 67 millivolt, okay? Which means if it was only sodium going in and out of the cell, that's where the membrane resting potential would be at plus 67 millivolt, which means that sodium always wants to push towards that plus 67. And last, but certainly not least, my calcium, 2 plus for calcium, it's 100 plus 123 millivolts, a very positive ion, and it wants to push my cell to go as high up, as close as possible to 123 millivolts as it can. So my pacemaker cells, they don't have resting action potential per se, because simply they don't rest. So we're just going to have a starting point of approximately minus 60 millivolt, and you will understand why towards the end. So we're going to start at roughly here, which is like minus 60 millivolt. So what's going to happen at that point? Well, look at our pacemaker cell down here. Yeah, pacemaker cells, they are attached to each other via gap junctions and leaky channels. Yeah, so these gap junctions, these leaky channels, are constantly open and then allow for a constant, slow influx of ions. And in the case of a pacemaker cell specifically, these are sodium leaky channels. If they're leaky channels, they're constantly open. So through here, I have a constant trickle of potassium, not a huge amount, but slowly it just keeps on coming in. Now if I have a small trickle of potassium getting into my cell, what's going to happen to the voltage of my cell? Well, obviously it's extra positive charges, so it's going to start to depolarize and go really closer to this plus 67 millivolts, because that's where sodium wants it to be. Yeah, so I'm just going to start it's going to start going up the way, not too fast actually, we'll do it even slower. Here we go, it's going to start going up the way slowly, because of this small trickle of sodium inside the cell. And how far up is it gonna go? Well, it's gonna reach approximately minus 40 millivolts. When it gets to minus 40 millivolts, something happens. At minus 40 millivolt, it's what we call a threshold. And this threshold is for my voltage gated ion channel, and to be precise, is a voltage gated calcium channel to open up. So here I've drawn on this other cell these voltage gated calcium channels, which they were there before, obviously, but so they don't just appear, but at minus 40 millivolt they open up. So we'll just note that here at minus 40 millivolt, my voltage gated calcium channels open up. Now, if my voltage gated calcium channel open, what is going to happen? Well, naturally, I'm going to have a significant influx of calcium inside my cell, like quite a lot. Okay, what is this going to do to my my action potential? Naturally, it's going to push it up even further, but faster than it did originally. Yeah, not as fast as it would do, as you will see later on in a contractile cell, but it's still quite fast until it reaches another threshold point, which is plus 10 millivolts instead. Okay, so at plus 10 millivolts, this is another threshold. I'll just do this way. Here we go. And here, two things will happen at plus 10 millivolts. So if you see here, at plus 10, my calcium voltage gated ion channels, they will close. So plus 10, my voltage gated ion channel close. Okay, but my potassium ones will open up. So my potassium voltage gated channels open just this way, allowing for what? Allowing for potassium. What does it want to do? It wants to go out of the cell, doesn't it? Because there's loads of potassium inside. And let's have a look. So there's potassium that tries to get out of the cell as much as possible, yeah? And it wants to push my threshold, my action potential down to this minus 92 millivolt, doesn't it? So what's going to happen here? Because there's no longer this influx of calcium, once I reach my plus 10 millivolts here, my voltage is going to start going down again a bit. Here we go, like that, until it's going to reach what? Where I started, minus 60 millivolts. That's where I started, wasn't it? And here, what happens at minus 60? Well, as you can see here again, potassium. Apologies for the wobbly. Here we go. That's nice and zoomed up. Potassium channels close at minus 60. Which brings me back to what? Well, it brings me back to my first cell here. So what's going to happen at this point? Well, what's going to happen at this point? I'm going to have this constant leak of sodium coming in, and my action potential will then start all over again. It's very slowly going up, reach minus 40, where my calcium voltage gated channels will open up, and it's going to be a little faster going up. It's going to reach +10. Calcium's going to close, and we're going to go back down to -60, and so on and so forth. What we have here is the generation and propagation of my action potential in a pacemaker cell. Let's not forget this. So from here to here, here we go. This is equates to 1 heartbeat. So in a normal heartbeat of about 60 beats per minute, this equates to roughly 1 second. So, well, here we'll put it. That is roughly 1 second that we do here. And this is the action potential of my pacemaker cells.